Hello. The topic of this video is algorithm analysis. This is quite different in flavor from all the lectures that you have seen so far. In all the previous lectures, we have studied some feature of the C programming language and what is the utility of that feature and how we can use that feature in various programs. This is what we have done in all the previous lectures. This lecture, on the other hand, is not directly related to the C programming language. This is related to computation in general. Algorithm analysis. What is an algorithm? An algorithm is a clearly specifiable set of instructions to solve some problem. For example, let's consider the problem of finding the GCD of two integers. An algorithm for solving this problem is as follows. Let's say the numbers are n1 and n2. The first step is you divide n1 by n2 and obtain a remainder. The second step is that you update n2 by n1 and n1 by the remainder of the preceding division, and you continue. So let me say it once more. In the first step, you divided n2 by n1. So step 1, you divide n2 by n1 and obtain a remainder r. The next step, you divide n1 by r and obtain a remainder r2. So what did we do in step 2? n1 now plays the role of n2 in the preceding step, and r plays the role of n1 in the preceding step, and we obtain the remainder r2. Let's say this remainder is r1 after the first step. The next step, we divide r1 by r2 and continue. And we continue till the remainder becomes 0. At that step, we return the divisor of the last division that we performed. And it turns out that the output of this algorithm is always equal to the GCD of the two input numbers. Given a problem, the first step is decide that the algorithm is correct. So this is the first step that we should be sure about, that this sequence of steps that we described eventually produces the result that we want, that is the intended result. This is the first step. And this step-by-step procedure is called the algorithm. Here I described the algorithm in language and took some small example, symbolic example, n1, n2, r1, etc. There are more formal and well-defined ways of describing algorithms. For example, by a flowchart or by a pseudocode. In this course, so far, you have implemented various algorithms in the C language using various features of this language. Those are implementations of algorithm. Algorithm is a slightly higher level object which describes the steps that needs to be performed and in which sequence and the sequence in which those steps need to be performed to obtain the desired output. The topic which is the subject matter of this video is determining how much resource the algorithm will require. There are various kind of resources that researchers study. The two dominant ones are time and space. What is time? It's just the amount of time that a program takes to run. The second resource is space. which is the amount of space that the program takes to run. That is the number of bytes in main memory, for instance. Yeah. Now, speaking of time, so far you must have seen in all the programs that we have written, at least the ones that we have talked about, the output is produced immediately. Like the moment you press enter, you see the output showing up on your screen. This is because in all these examples, we have run our programs on really small inputs. Yeah? Inputs, arrays of length at most 10. Yeah? Numbers whose magnitude is at most, magnitudes are at most something. At least for a number to be stored in an integer variable, its magnitude cannot exceed 2 power 16 minus 1. 2 power 16 in unsigned integer, and so on. But as the input size grows, the program will take more and more time, and once the input size becomes very large, so that delay will become observable. You will see your program taking time and outputs showing up after some time. Perceptible the delay. Yeah. Okay. How much resource is required? Measures of efficiency, execution time, which is often called time complexity, and memory space, which is often called space complexity. This is a fundamental observation which we made in the last slide, which is that the larger the amount of input data, the larger is the amount of resources it requires. So the amount of resource, let's talk about computation time. The time required is generally an increasing function of the amount of input data. Yeah? We will see some examples soon. So complexities. Same is the case with space. As the size of the input data grows, your program is expected to take more and more space. Now, we would like to come up with some useful measure of complexity of an algorithm. That is the amount of resource that an algorithm takes. Now, what do we use for a yardstick? This is the question. Well, the same algorithm will run at different speeds and will require different amounts of space when run on different computers, different programming languages, and different compilers. But I'd like to attach a measure to the algorithm. I'd like to attach a measure that will measure the complexity of an algorithm regardless of the machine that you are running it on or the system softwares that the program is being run on. I'd like to have a measure that is independent of the platform on which you are running your algorithm. How do I do that? Now, we again fall back on the observation that we made. Algorithms usually consume resources in some fashion that depends on the size of the problem they solve, which we will denote by n, small n. Small n will stand for the input size. And the dependence on the amount of consumed resources on the input size is what we are looking to capture. Let's take an example. This is a very basic sorting problem. This C function sort takes in an array and an integer, which denotes the size of the array, as arguments, and it sorts the array. What does it do? Well, there is this outer for loop that has a variable I going from 1 to n, incrementing, and which is incremented in each step by 1. And in the inner loop, there is another variable j that starts from I and goes backward till 0. Yeah? And as long as you find array elements which are larger than your current array element, which is AI. So we have AI copied in this variable X, yeah, and then we are traversing the array backward, starting from I. As long as we see array elements aj minus 1, which are greater than X, we keep going left and keep shifting those elements to the right. We are here looking to insert AI in an appropriate position in the array. So we stop when either the array ends, that is we hit the leftmost element of the array, or we have found an element which is less than or equal to X. Then we set aj to X. So this element X is now inserted in the right location of the array, and after this iteration of the while loop, A0 through AI are sorted in the right order, increasing order or non-decreasing order of magnitude. Yeah. This is the sorting algorithm. Now, we run this sorting algorithm on two different computers, and note the time in millisecond for different sizes of input. Size of input here refers to the size of the array that you are running it on, that is the value stored in this integer variable capital N. Yeah? And this table lists the time that this sorting algorithm takes on two different computers. See here, the numbers are pretty different. So computer 2 seems to be much more fast than computer 1. On an array of size n, computer 2 takes 2.8 millisecond, while computer 1 takes 12.5 millisecond. When the array size is 250, computer 2 takes 11 millisecond, while computer 1 takes 49.3 millisecond. Yeah? Now, if we want to measure the complexity of this algorithm in terms of the time it takes to run on arrays of various sizes, then that measure is dependent on the machine that we are running it on, as this table shows. It depends on whether I am running the program on computer 1 or computer 2. Yes? Sorry. However, let's observe the way in which these numbers grow as we go down the table, which is as the input size grows. Yeah. Okay. So here, for instance, let's look at the second column that corresponds to computer 1. On arrays of size 125, it takes 12.5 millisecond. On arrays of size 250, it takes 49.3 millisecond. So the array size has gone up by a factor of 2. 250 is twice 125. But the computation time has gone up by a lot more than a factor of 2. It has gone up roughly by a factor of 4, if you observe. Roughly speaking, not exactly. Now when the array is 500, it takes 195.8 millisecond, which is, again, you will see, roughly equal to 16 times 12.5. So when array size goes up by a factor of 4, 500 is 125 times 4, computation time goes up roughly by 16. So you can see a pattern. Array size, when array size doubles, computation time goes up by a factor of 4. When array size goes up by a factor of 4, computation time goes up by a factor of 16. And you probably see where it's going. So if the array size goes up by a factor alpha, computation time tends to go up by a factor of alpha square. Again, roughly speaking, not exactly. How about this column? 11 is less than 2.8 times 4, but roughly speaking of the same order. 43.4 is less than 2.8 times 16. Is it less than? Around that magnitude, maybe slightly less, but you can see the same pattern here also. So although the numbers look very different, the way it grows with the input size is similar in both the machines. So this is the key to actually analyzing the performance of the algorithm lies in this observation. So irrespective of which machine you run it on, the way it grows as the input size grows is similar in both the machines. Now, this is the exact expression, let's say, for the two machines. F1n is the time that computer 1 takes, the time that our program takes to run on computer 1 on arrays of size n. F2n is the time that our program takes to run on an array of, to run on computer 2 on an array of size n. Yeah. And these are the expressions. Now, these expressions, you will observe that both are quadratic polynomials, degree 2 polynomials of n. Yeah. Here, the coefficient of the leading monomial, which is n square, for computer 1 is much larger. Here, it's much smaller. Yeah. This is roughly why computer 1 takes less time than computer 2. But since both are quadratic functions of n, if we ignore these terms, linear and the constant term, as you can see, they will become more and more insignificant as n grows. The leading term will dominate them and their influence will be less and less as n grows. So roughly speaking, if n goes up by a factor of 2, n square goes up by a factor of 4 and so on. This is basically the reason why we saw computation time to go up by a factor of alpha square when the size of the input goes up by a factor of alpha. So both are quadratic functions of n. Now the shape of the curve that expresses the running time as a function of the problem size stays same. So what do these curves look like? So it's a quadratic polynomial. So both of these are parabola. So if I plot, on the x-axis let me plot n, that is the input size. On the y-axis let me plot f1 or f2. Then if, let's say, for a moment assume that these terms are not present, only it's some constant times n square, then the curves would have looked like this. One curve would have looked like this and the other curve would have looked like this. This is the curve for computer 1. This is the curve for computer 2. Now, because of these lower order terms, these curves will be slightly shifted to the right. It may look now like this, one curve like this and one curve like this. But the point I want to try to emphasize here will make it more mathematically formal and solid very soon. But for now, the shape of the curves, the shapes are similar. The shape of the curve that expresses the running time as a function of the problem size stays the same. Okay. So, complexity classes. The running time for different algorithms, they tend to fall into different complexity classes. Each complexity class is characterized by a different family of curves. So, both these curves fall in the same family of curves, which is the quadratically growing curves, parabolas. And all curves in a given complexity class share the same basic shape. So it's a basic shape. Is like this. Some grow slightly slower, some grows faster, and that may depend on the machine that you're running it on. But the basic shape remains the same, and it's largely independent of the machine or the software platforms that you're running your program on. The order notation, we'll see soon, is used for talking about the complexity classes of algorithms. So let's introduce the language of big O notation, big O. For the quadratic function, fn is equal to an square plus bn plus c, where a, b, and c are constants, we will say that fn is order of n square. So it grows, so this roughly speaking, it says that it grows quadratically with the size of the input. Now, the specific constants that sit before these monomials may be different, but the dependence on n is quadratic. we focus on the dominant term and ignore the lesser terms, and we throw away their coefficient. We'll make it formal soon, because again, roughly speaking, the intuition is that when n grows, becomes very large, an square will be much bigger than bn plus c. So bn plus c will lose importance as n grows, and their importance will soon become insignificant, so you can just discard them. Okay, so this is the formal definition. We will say that a function Tn of n, so think of capital N as the input size, which was small n here. Think of capital N as the input size. We will, and Fn is some other function of capital N. So Tn will say is order of Fn, big O of Fn, if there are positive constants c and n0 such that Tn is less than or equal to c times Fn when n is greater than or equal to n0. Yeah. So let's take an example. So in this example, yeah, let's look at F1. Yeah, you will be able to prove formally, I leave it to you, that F1n is less than or equal to, let's put a constant which is slightly bigger than this. It's okay. So let's put 0.001 n square for all large enough n square, large enough n. For some initial small values of n, F1n might be greater than this written on the right hand side, but you will be able to work out some n0 such that the moment n exceeds n0, n greater than n0 for some n0, the moment n exceeds n0, this function will take over F1n. So F1n will be less than or equal to 0.001 times n square for all but few small n's. So when this holds, we will say that F1n is order of n square. So this corresponds to the constant c that we saw there. Let me point it out again. This constant c. So Fn, so in that example, capital Tn is F1n, c is 0.001, and Fn is n square. So in the last example, this is F1 of n, this is 0.001, and Fn is n square, and F1n is less than or equal to 0.001 times n square whenever capital N, so let me write capital N, whenever this capital N is bigger than some n0. That n0 you work out yourself. I will not do it. That's left to you as an exercise. So the idea is that if I leave out some initial small values of capital N, then Tn will be dominated by some constant times Fn. Now this constant, we are not saying anything about the value of this constant, but it's a constant. It's not something that grows with n. It's some fixed constant. It is independent of n. So this roughly means that as n increases, Tn grows no faster than Fn. The function t is eventually bounded by some multiple of Fn. Yeah. So F1n is eventually bounded by 0.001 times n square. Eventually. The function t, so Fn gives an upper bound in the behavior of Tn in this particular sense that we said. Okay. So in the initial values, for instance, if n equal to 0, 0.001 times n square is 0, but F1n is not 0, it's equal to 0.001. So even when there is no element in the array, the computer takes some time, perhaps to realize that there is no element, but that's some amount of time. Computer 2 takes longer, much longer, 1000 times longer when n is equal to 0. But in the long run, computer 2 is much more efficient because this constant is much smaller. And in general, whenever the runtime is of the form an square plus bn plus c, we will be able to say that the function is order of n square. because the lower order terms will not matter. Here is another notation. Tn is omega of gn if there are positive constants c and n0 such that Tn is greater than or equal to c times Fn. For large enough n, if you leave out the first n0 numbers, then Tn will be lower bounded by some constant time Fn. Yeah. So here, for instance, F1n will be less than or equal to let's say 0.1 n. Yeah, eventually. So eventually, if it's going to be, I'm sorry, greater than or equal to 0. For large enough n. Again, you will be able to work out some constant n0 prime, since I called n0 here. N greater than or equal to n0 prime. I'm putting the prime to distinguish it from n0 that I have written here. This is because the right hand side is a function that grows linearly with n. On the other hand, the left hand side is a function that grows quadratically with n. So the left hand side is a faster growing function. So eventually, it will overtake the right hand side function and will continue to dominate the right hand side function throughout. So as n increases, Tn grows no slower than Gn. Tn grows at least as fast as Gn. Yeah? Okay. Let's proceed. One more notation. All these notations are like of the same spirit. Once you understand one, the other definitions shouldn't take you too long. Tn is equal to theta of Hn, so capital theta, if and only if Tn is equal to order of Hn and Tn is equal to omega of Hn. Yeah? So that means that n increases, Tn grows exactly as fast as Hn. So Hn captures the growth of Tn. It's upper bounded by some constant times Hn for large enough n, as well as lower bounded by some constant, maybe a different constant, times Hn for large enough n. So in this example, both F1n and F2n are theta of n squared, So I said that F1 is at least 0.01 n. I can also say that F1n is at least, put in some constant which is slightly less than this one. So let's say 0.0001 n squared. You'll be able to show this also for large enough n. So for large enough n, F1n is upper bounded by some constant times n squared here, as well as lower bounded by another constant times n squared. So F1n is equal to theta times n squared, we'll say. Okay, little o. Tn is equal to little o of Pn. If Tn is equal to order of Pn, but Tn is not theta of Pn. That is, Tn is upper bounded by some constant times Pn, but Tn grows strictly slower than Pn. Tn cannot be lower bounded in terms of Pn, like a constant times Pn. So, for example, here, F1n and F2n, both are little o of n cube. Since they are upper bounded by 0.001 times n square for large enough n, they will also be upper bounded by 0.001 times n cube also. But I will not be able to lower bound it by any constant times n square, n cube. That is not possible because it's a quadratically growing function and n cube is a cubic polynomial. So it will grow strictly faster than any quadratic polynomial. If once n becomes large enough, it will overtake any quadratic polynomial. Okay. Here is a nice way to visualize this. Limit as n tends to infinity, Tn by Pn is equal to 0. So Tn grows strictly slower than Pn So the ratio Tn by Pn becomes smaller and smaller as n increases, and it can be made arbitrarily small by choosing large enough n, and it becomes 0 in the limit. Here are some examples. Log of n with respect to any base, here base, the natural log of n, base e, is order of n. This is because logarithm is a slower function. It grows slower than linear. Yeah. So what does the curve for log look like? Yeah. So it's 0 when n is equal to 1, and then it grows something like this. It grows slower and slower, and the derivative, the slope of the derivative decreases. This derivative is like 1 over n, right? So it's a decreasing function of n. On the other hand, linear curve is like this. So it grows faster. You can even replace this big O by little o, no problem. N to the 10 is little o of 2 power n. N to the 10 looks like a very fast function, a degree 10 polynomial, but the right hand side is an exponential function of n. It's 2 power n. N is in the exponent. Here n is in the base while the exponent is a constant. Here the base is a constant while exponent is n. And exponential functions are faster than any polynomially growing function. Strictly faster. So n to the 10 will be little o of 2 power n. 3n square plus 5n plus 1 is exactly n square in terms of growth. Theta of n square we will say. And we have seen this example. f1n and f2n both are quadratic polynomials. We said that both are theta of n square. Concepts in analysis. So you will talk about various complexity measures of algorithms, worst case, average case, operator count, etc. Worst case is what? So we said that in this table, for instance, this is the time taken by this algorithm on arrays of size 125. But this time will typically be different for different arrays of this size, right? So what do I mean by 12.5? This is time taken on which array of size n? I should ideally mention that. Without this information, this statement is not complete. Yeah, so now it depends on what you mean. If you are talking about the worst case complexity, it means that the maximum time taken on any array of size 125. If you are talking about the best case complexity, it means the minimum time taken on an array of size 125. Average case means the average time taken on. If I compute the time taken on all the arrays of size 125 and then compute their average, that average is this. Operator count. Yeah. So for instance, like the number of operations that you do. For sorting algorithms, researchers are often interested in the number of comparisons that you perform. You count only comparisons, and that is your measure of complexity, not other computations. Comparison is the only thing that you care about, for instance. Why is the analysis of algorithms important? Computer hardware is advancing all the time, right? So computers are becoming faster and faster. So do we need to actually put in effort to design fast algorithms? Or should we instead focus entirely on improving our computer hardware? Can advance on hardware overcome inefficiency of your algorithm? The answer is no, a resounding no, and we will soon see why. A normal computer, instructions executed sequentially. Yeah. In C program, for instance, we write a program and the program is executed one statement at a time from the beginning of the program. Yeah. And then due to function calls and all, there are jumps and so on. But the basic format is sequential execution. Even in machine levels, instructions are read sequentially and executed. And instructions in the machine level are basic operations like addition, multiplication, comparison, assignment, etc. We assume that they all take just 1 unit of time. That is not strictly true. Multiplication, for instance, is more expensive than addition, potentially, and so on. But for simplicity, and so far as for simplicity, we assume that they all take unit time. And so far as those order notation that we introduced a few slides back, so far as those are concerned, this assumption does not make a difference. So you can safely assume that all instructions take a single time unit. Okay. So let's now convince ourselves that advances in hardware do not necessarily fix inefficient algorithms. So let's assume that in a machine, the speed is 10 to the power 7 instructions per second. Yeah. Now this is a table that lists the time taken by this machine on inputs of various sizes. So if the size of the input is n, So these are let's say the runtime of 5 different algorithms. So the first algorithm takes n time, the second algorithm takes n log n, and so on. So n is the most efficient. After that, n log n, n squared, n cube, and this is an exponential time algorithm. And these are the various values of n. Yeah. So what is, for instance, this entry? So this is the amount of time that this algorithm takes on an input of size 30. Yeah. Now, if I look at this row, this corresponds to the time taken by an algorithm which runs in linear time n. So it grows linearly. So on inputs of size 10, it takes 0.001 millisecond. On inputs of size 20, it takes 0.002 millisecond, and so on. And inputs of size 10,000, it takes 1 millisecond. Now, once the input size becomes n log n, you can see some difference. Yeah. And it also grows faster than linear. Here, the input size has gone up by a factor of 2, but the time taken has gone up by more than a factor of 2, and so on. So on inputs of size 10,000, it takes 13 milliseconds. So this is the table. So an n cube time algorithm takes 28 hours on inputs of size 10,000. Yeah. And a 2 power n times algorithm takes like forever, really. Like it's not even written here. This is already prohibitively large, even for inputs of size 100. Yeah. Okay. Now let's do another exercise. Let's consider 3 different machines. The first one runs in speed s, which is 10 to the power 7 instructions per second. The second one is 100 times faster, and the third one is 1000 times faster. So how do these algorithms do on these faster machines? Okay. So now, what are these n1s? So n1, n2, n3 and n4, these are the maximum size that are solvable within 1 hour. So n1 is the maximal size that this algorithm can solve within 1 hour, and so on. Yeah? So now, as speed becomes 1000 folds, you can solve 1000 times bigger instances in 1 hour if you are running this algorithm that runs in linear time. That's a fantastic improvement. If you are running this algorithm, if the speed becomes 1000 fold, then you cannot handle 1000 times bigger instances. You can only handle 750 times bigger inputs. So you see the improvement, the factor is less than 1000. So if the speed goes up by a factor of alpha, the size that you can handle goes up by a factor less than half. And this factor becomes worse and worse as the runtime increases. If you are running an n squared time algorithm, the size that you can handle goes up only by 30 times. You could handle 2 times 10 to the power 5 sized instances in 1 hour. Now you will be able to handle 30 times as many. The size is 30 times 2 times 10 to the power 5. Now if your algorithm is hopelessly slow, exponential time, you will be able to handle only instances. Earlier you were being able to handle instances of size 35. So you were doing very bad. Here, this algorithm was being able to handle inputs which are this big. Imagine 3.60 to 10 to the 10. On the other hand, you were being able to handle only instances of size 35 in 1 hour. And now you'll be able to handle instances of size 45. The speed has gone up 1,000 times. Yeah. But your capacity has not gone up at all, almost. Yeah. It's almost as if you are very, very aware. This 2 power n is such a fast growing function that if 1 hour is all that I allow my algorithm, and if I look at the size that it can handle in 1 hour, that number hasn't gone up much at all. Like, it can handle instances of size 45. So this means that this advance in hardware has not benefited this algorithm at all. So there is a big difference between polynomial time complexity and exponential time complexity. So generally, polynomial complexity is the notion that is used to capture efficient computation. Polynomial means n to the some fixed constant, n square, n cube, and so on. And this is not polynomial, this is exponential. And you can see. So hardware advances affect only efficient algorithms and do not help inefficient algorithms. Clearly, you can see that. So this algorithm is greatly benefited by these advances in hardware, but this improvement in hardware has almost no effect on this algorithm. So let's consider a problem. It's called a maximum subsequence sum problem. What is this problem? Let's see. So you are given n integers a1 through an, and you want to find the maximum value of such a sum, k equal to I to j ak. So a1, a2, a3, and so on, you are given an, and you want to find out a block here where it begins at ai and ends at aj, such that the sum of everything in this block is maximum amongst all possible blocks. Yeah. Now, if all the numbers are non-negative, then it's a trivial problem. This block is always your answer. If the number is non-negative, all the numbers are non-negative. This is if all are non-negative. So the problem is interesting only when there are negative numbers. Yeah. And for convenience, the maximum subsequence sum is considered to be 0 if all the numbers are negative. If even one number is positive, the maximum subsequent sum is greater than or equal to 0, non-negative. Why is that? Well, you can just choose the block that contains just that number. So let's say A3 is non-negative. Then you can choose this block. This is a block whose sum is non-negative. And there can be other blocks. But certainly there is one block whose total sum is non-negative. So the answer is non-negative. So here is an example. If your sequence is -2, 11, -4, 13, -5 and 2, the answer is 20. A2 to A4. Yeah. So this 13 plus 11 is 24, minus 4 is 20. Okay. So here is a very basic algorithm for solving this problem. This is probably one of the first thing that one would think if one is presented by this problem. So basically you go over all blocks and see which one gives the maximum sum. So max sum is initialized to 0. And then you consider all possible all possibilities for I and j. So I begins from 0 and goes up to n minus 1. J begins from I, because j is at least I, and goes up to n minus 1. And in this loop, in this innermost for loop, you compute the sum of ai through aj. Yeah, this sum is initialized to 0, and in each iteration of this for loop, you add ak. K is initialized to I. K increments all the way up until j, and this sum is computed. And once you exit the for loop, this sum holds. This variable, this sum holds the sum of ai plus 1 till aj. Now, max sum holds the biggest subarray sum that we have found so far. If this subarray sum is more than max sum, you update max sum. And once you come out of the loop, you know that max sum holds the maximum subarray sum, which is what you return. Okay. So, the loop at line 2 is of size n. So, what does it mean? So, this loop runs for, so the number of iterations that it runs for is n. So, 0 to n minus 1. The second loop has size n minus I. So, it's number of iterations. Size meaning number of iterations. So, n minus I. So, it depends on the value of I. So, as initially I is 0, so it runs for n iterations. As I increases, it runs for less and less iterations, and so on. So it goes from I to n minus 1, so n minus I iterations. And the third loop has j minus I plus 1. So this loop, it depends on both I and j. So this loop, k goes from I and goes till j. So k takes j minus I plus 1 values. And for every setting, you do some amount of work here. So the number of iterations is j minus I plus 1. Now, in each iteration, there is addition and assignment. We will say that you do one amount of work in one iteration of the innermost loop. Yeah. So the total number of work in the innermost loop is j minus I plus 1, which is just the number of iterations. As we said, in each iteration, we do constant one amount of work. So I'm just adding 1 for k equal to I to j. Total amount of work is j minus I plus 1. How about the outer loop? The outer loop goes from, let's fix an I. Let's look at one particular iteration of the outermost loop. Now look at this for loop. How long does this for loop take? For a fixed value of I, how long does this for loop take? So this for loop has n minus I iterations as j goes from I to n minus 1. And for a fixed value of j, we just saw, we spent j minus I plus 1 time. So the total amount of time that this for loop takes is the summation of this number over all possible values of j. And this is, arithmetic progression, and the sum is this: n minus I plus 1 times n minus I by 2. Yeah. Basically, j minus I goes from 1 to n minus 0 to n minus 1. So it's basically the sum of 0 to n minus, j minus I goes from 0 to n minus 1 minus I. So it's basically the sum of first n minus I plus 1 integers. The first n minus I integers. And this is the AP series. So, this is the amount of work that each iteration of the outermost for loop does. This is the amount of work that done by each iteration of the innermost for loop is 1. The amount of work done by each iteration of the second for loop is j minus I plus 1. The amount of work done by each iteration of the outermost for loop is n minus I plus 1 times n minus I by 2. So what is the total amount of work? Well, the total amount of work done by all iterations of the outermost for loop, which is this quantity summed over I from 0 to n minus 1. And this you do yourself. It's sum of squares of first n minus 1 natural numbers and sum of first n minus 1 natural numbers. You apply those formulas and this is what you get. So this is basically the runtime of your algorithm. You see where it's going. The runtime is, this is order of n cube. So it's a cubic time algorithm. Now, let's improve our algorithm. Now, you observe this. So there is some repetition in this computation. Yeah. We are computing some subarray sums repeatedly and not utilizing previous computations. So here, this is a very basic observation. Sum over k equal to I to j of ak is aj plus sum over k equal to I to j minus 1 ak. I'm just writing the last term of the sum separately and adding over the remaining terms in this summation. Okay. So using this observation, we can greatly improve the complexity of the program that we wrote before. So let's go over it. So here max sum is initialized to 0, and now here is a for loop where I have a variable that goes from 0 to n and which is being incremented by 1 in each step. And in each iteration of the for loop, let's try and understand what it does. There's this variable this sum that's initialized to 0, and j is a variable that begins at I and is incremented in each step till n minus 1. Okay. Now, and you increment this sum plus you increment this sum by aj. Now, in the first iteration, let's say, of this for loop, so this sum is 0. In the first iteration, what have you computed? You have computed the subarray sum of just this subarray of size 1, which is ai. Yeah? This is one subarray sum that you have computed. Now, max sum, in the max sum you are maintaining the maximum subarray sum that we have seen so far. So it makes sense to compare this sum with max sum and see if this sum is greater than max sum. If it is greater than the max sum, you update max sum. Now you go back again. So it's not properly indented, I'm sorry. So this is the body of this inner for loop. Okay. So then you advance j again. So j becomes I plus 1. This sum had ai in it. Now it adds to it ai plus 1. So now this sum holds the subarray sum of this subarray of size 2, that is ai and ai plus 1. You again compare this sum with max sum and update max sum if necessary. Yeah. So now you see we have actually considered all subarrays. In the outer loop, we consider the starting points, all possible values of I, and in the inner for loop, we consider all possible values of j. And for all possible values of j, we have actually considered the subarray that lies between indices I and j. But we have spent much less time because we are using this observation. Yeah. Because to compute the sum of ai and ai plus 1, I am making use of the sum of the subarray ai, which was pre-computed. I am just adding aj to it, ai plus 1 to it. Yeah. So its complexity is order of n square. Well, because why? Because in a particular iteration of this for loop, the number of the outer for loop, the number of iterations in the inner for loop is n minus I. And in each iteration, it does some amount of work. It's a C time. C is some constant that does not depend on n. Yeah, it's basically an addition, an assignment, comparison, another assignment, and so on. Whatever time it takes. So the total time is this C added from j equal to I to n minus 1. and then so which is basically n minus I plus 1, sorry, n minus I, c times n minus I. Yeah, this is the amount of time. And then the outer for loop, this is the amount of time spent in each iteration of the outer for loop. So the total time spent by the algorithm is summation of this, and you will be able to convince yourself that this is order of n square. In addition, there are some constant amount of work which we ignore because they will introduce some constant factors here and will not matter for this big O. Okay, so this solves the same problem but is a better algorithm. It improves the cubic runtime to a quadratic runtime. Okay, recursive algorithm, divide and conquer. Yeah, we have done such algorithms, such programs we have written in this course. So it has two steps: divide, which is split the problem into two roughly equal subproblems, which you solve recursively. And then you solve the problem recursively on those subproblems, you obtain the solutions on those subproblems, and then you sort of combine those solutions together to obtain a solution of the original problem. And some more work. This is the conquer step. So it has two steps, divide and conquer. And we have seen such algorithms. Now we'll use this divide and conquer principle or algorithm design paradigm to design an even better algorithm for the maximum subsequence sum problem. Now the maximum subsequence sum problem, so this is the array that's given to you. Now roughly speaking, we'll break the array into two parts. The maximum subsequence sum can be in one of the three places. It occurs entirely in the left half of the input. It could be here. It could be here. Or it could actually intersect with both the halves. It crosses the middle. These are the three possibilities here. Now, if I divide the array into two equal halves and solve the maximum subsequence sum on each of these halves recursively, I will be able to get hold of these two cases. Yeah. So if I solve the maximum subarray recursively on the first half, I'll be able to find the maximum subarray sum of the first half of the array. Similarly, I'll be able to get the maximum subarray sum of the second half of the array by a recursive call to the same function on the second half of the array. Now I'll have to do something about these subarrays that crosses the middle of the array. So 3 can be solved. So 1, 2 and 3. So 1, 3 can be solved by finding the largest sum in the first half that includes the last element of the first half, and the largest sum in the second half that includes the first element of the second half, and adding the two. So what is 3? 3 is basically, you look at the largest sum. Let me use a different color, maybe black. 3 is, you find the largest sum that starts in the middle and goes left. The largest subarray sum of this form, and you also find the largest subarray sum of this form and put these two together. This is what 3 will necessarily look like. Yeah. So this is going to be the conquer step that you do. So let's put these ideas together and write a C program. This is a illustrative instance example. Okay. So if left, okay, so here there is a function max sum. It takes in an array. It's going to be a recursive program. So from your past experience, you will guess that it will have to be passed. It will be convenient to pass the program the left and right indices of the array. So initially we'll pass 0 and n minus 1. Inside the recursive calls, you will pass various other indices. So if left is equal to right, that means that the array has only one element. You check whether that element is strictly greater than 0. If it is, then you return that element. Otherwise, you return 0. Because by definition, if all the elements are negative, we defined maximum subarray sum to be 0. Now center is left plus right by 2, which is the index of the middle element of the array, plus minus 1. Now, you recursively run your program on the left half of the array and also on right half of the array. Yeah, you obtain those values. Just a minute, please. Yeah. Now, after you obtain those the solutions to the subproblems, then those are stored in these two variables, the maximum subarray sums, max L sum and max RT sum. Now you do the conquer part. So in this portion, so this is not the end of the program, it continues to the next slide. So in this page, so you first look at all the arrays that are of this form, this black array. So you start from the center and go left and look at all these sums. If for each of those sums you check whether it's greater than the running maximum that you are maintaining, and if it is, then you update it. And after this, max LB sum will contain the sum of the maximum subarray sum, which is of that form. Similarly, in this for loop, you compute the maximum subarray sum, which is of the other kind. Of this kind. Yeah. And what you do is you return the maximum of these three, max XL sum and max L sum and max RT sum are from the recursive calls of the two halves, and this sum is the total sum of the two black subarrays. Yeah, so we should really be returning the maximum of these three numbers, which is what we did, which is what we do. Yeah. I think there is a slight mistake in the naming of this function. So it should be max sub sum. Okay. And here max sub sum. Okay. How much is the complexity of this program? Okay, let's see. So for convenience, let's assume that the size of the array is a power of 2. It's a 2 power k. It will not matter if you put a order. Yeah. So let's look at this conquer phase. How much time do you spend in this conquer phase? So this is basically the conquer phase, right? These two for loops. Yeah. So you start from the center and go left and right to the beginning and to the end of the array. So the amount of time you spend is proportional to the total amount of time you spend is proportional to the total number of elements in the array, which is n. So you will say that the total amount of time in the conquer step is some constant c times n, which is what you see here. So if I denote by tn the time taken on an array of size n, I can express tn in this form. So what is the time taken by the first recursive call? It's t of n over 2, because it runs on an array of size n over 2. The second recursive call, again t of n over 2. So in total, we have 2 times t of n over 2. And the conquer step takes c of n time. Yeah? Now if I draw a tree, for instance, so a1 through an. So this is a node in my tree. I will write here the time taken by the conquer step. So A capital N, let me write. Time taken, the conquer step is C times N. Yeah. So let me write, as I said, N is a power of 2, I'm going to assume. So N is 2 power K. So this is C times 2 power K. Now in the next step, you do a recursive call on A1 through A 2 power K minus 1 and A 2 power K minus 1 plus 1 to A 2 power K, right? What is the total conquer time? So here you spend C times 2 power K minus 1. Here also you spend C times 2 power K minus 1. So in total, in this level, you spend C times 2 power K. Yeah. Let's do one more step. Let me write it here. So here you will again recursively run your function on two subarrays A1 to A times A of 2 power K minus 2 and then here A 2 power K minus 2 plus 1 to A 2 power K minus 1, and then in this array also you will recursively run your program. So let me write in the next line for want of space. A 2 power K minus 1 plus 1 to A 2 power K minus 1 plus 2 power K minus 2. And the final, so the second half of this second half, the second half of the second half of level 2 is A 2 power K minus 1 plus 2 power K minus 2 plus 1 to A 2 power K. Yeah. So you see in each of these you have 2 power K minus 2 and array elements. So you will spend C times 2 power K minus 2 time in each of them in the conquer phase. Yeah. So C times 2 power K minus 2, C times 2 power K minus 2, C times 2 power K minus 2, C times 2 power K minus 2. In total, you will spend C times 2 power K. So you can see that in each step you will spend the same time. You can go further down the tree and extend this argument. You will see that the total amount of time you spend in the conquered steps is C times 2 power K. And if you really expand the recursion, you will see that in some level all the time is spent in conquered steps at some level. So the total amount of time is really the sum of these numbers, 2 power K, 2 power K and so on. How many levels are there? So in each level, the size of these blocks goes down by a factor of 2. So in K level, each block will have only one element. Yeah, 2 power K divided by 2 power K. So the number of levels, and then if you have a block of only one element, you will just solve it. You no more further recursive calls. So the number of levels is K, and in each level you spend C times 2 power K steps. So number of levels is K. So the total time, let me use the order notation here, order of K times 2 power K. Now what is K? N is equal to 2 power K, we said. So K is equal to log n to the base 2. So this runtime is really order n log n. So you have got an n log n time algorithm. Earlier we had an n squared time algorithm, and it's an improvement because log n grows much slower than n. So n log n it grows slower than n times n. So we have improved this algorithm. it turns out that you can improve it further. Here is a linear time algorithm, and this is basically the best you can do, because you cannot hope to find an algorithm that runs in less than n time, because to even look at the entire array you will need order of n time. So what does it do? Well, there is an outer for loop that goes over. So there is an index j that starts from 0 and goes till n minus 1, incrementing in each step by 1, and then you maintain the cumulative sum. Yeah. So initially, this sum is initialized to 0. Max sum is also initialized to 0. And as you traverse this array, you add the array elements to this sum. This sum is the running sum. Now, as long as this sum is bigger than max sum, you keep updating max sum. But if this sum becomes less than 0, then you just reset this sum. You just set it to 0. Which in spirit means you are discarding the portion of the array that is to the left of this sum, and you are starting all over again. Now, yeah, it's just one for loop and a constant amount of work inside it. So it's pretty obvious that it takes order and time. But it takes a bit of a work to argue that it indeed returns you the maximum subarray sum. Yeah. So this is one example where actually establishing that the algorithm is a correct algorithm takes some work. Yeah. It's not immediately obvious. However, that is kept in this presentation. Thank you.